Today we're going to be looking at the total area between the curve of a function and the x-axis. Now we've underlined total here because this is different than the definite interval. For the definite interval, you're looking at net area, meaning the area under a curve is negative. If you recall, for total area, when we did Riemann sums, the area under the curve is considered positive. So keyword total. Here's our graph, and we've already determined with Riemann sums that it looks like that total area is 4. Meaning this piece right here under is 4/3. This piece that's above the x-axis is positive 4/3. And this piece below is also positive 4/3. If we add 3 of those up, 3 times 4/3 equals 4. So let's confirm that analytically by doing some calculus. So how do we do it? Well, here again, here's our function, 1 minus x squared. Now the question is, how do we find the total area? Well, we are going to use the integral. We're just going to have to split it up. Here's the interval we're talking about. So it's from -2 to 2. Now the first thing I want you to notice, bouncing back and forth between this and our graph, is that it definitely matters where this crosses the x-axis. And I'm going to go ahead and circle these two intersections. Now why does that matter? Because if we were to just take the definite integral of the entire function from -2 to 2, what's above and below the x-axis are going to cancel each other out as far as negative and positive goes, and we're just going to get 4/3 back. Since we want to know the total area, it's going to help to know where these cross the x-axis, because if we can find the definite integral, say, of just this piece from -2 to -1, if we make that positive, so we know this is negative 4/3, if we make that positive and add and do the same thing for the other two pieces and make them positive, then when we add them all together, we will get the total area of 4. So basically just flipping whatever is below the x-axis as far as area goes, making it positive. What does it mean to make something positive? It means absolute value. So you see absolute value whenever you're talking about total area. So the first thing we need to do is find those x-intercepts so we know what to flip. So how do you find the x-intercept of this function? Well, you just set it equal to 0, and you solve. So what I would do is add x squared to both sides. You get 1 equals x squared. Scroll down here a little bit. Then you're just going to take the square root of both sides. Don't forget plus or minus. So you get plus or minus 1 equals x. It's going to be your x-intercept. That's just confirming what we see on that graph there, namely that it crosses the x-axis at -1 and 1. Again, this helps us to split up the integral into 3 pieces and just take the absolute value of each definite integral individually, which will give us the positive 4 that we're looking for. Alright, so step 2 is to determine the intervals of integration. Well, our original interval was from -2 to 2, so all we have to do is split up the interval based on these x-intercepts. So here are going to be our intervals. We're going to start at -2, which was our first, our leftmost interval x value, and we're going to go to -1, and -1 is the first x-intercept we ran. Okay, the next interval is going to go from -1 to 1. That's going to be our in-between interval, in other words, the interval between our two x-intercepts. The last interval is going to be from 1 to 2. So you can see that for every x-intercept you have, you'll have one more interval. In this case, I have 2 x-intercepts, so I'll have 3 intervals total. So 3 is to break up the integral in terms of the intervals. So instead of just doing the definite integral from -2 to 2, which would give the signed area, we need to split it up into 3 integrals. First integral, and these are going to be based on these actual intervals we just came up with. The first one is going to be from -2 to -1 of 1 minus x squared dx. Okay, however, as we said, that area is going to naturally be negative, as we can see. So whatever that definite integral is, we're going to have to take the absolute value of that. And again, if we go back to our graph, we can see why. We're going to get -4/3 back, okay? We're going to have to make it positive. In order to make it positive, we will take the absolute value. Now, the middle piece won't matter. It's going to be positive anyways, but might as well put the absolute value around it because most of the time you can't just look at it and tell whether it's going to be negative or positive. The third piece will be negative again. We'll put the absolute value around it. Okay, so there's our first way we break it up. The second way we're going to break it up is from -1 to 1. So this is going to be plus the definite integral from -1 to 1 of 1 minus x squared dx. And again, we have to take the absolute value of that. And then the last piece is going to be from 1 to 2. 1 minus x squared dx. And once again, we know this one's going to be negative, but even if it weren't, we'd still take the absolute value of that and add it. And so when you're finding total area, you want to break up the definite integral into the number of pieces it makes based on how many times it crosses the x-axis. And I should have one more absolute value bar here. It's going to look like that. Now we're going to determine the definite integral of each expression. Well, fortunately, the antiderivative of these isn't going to change. The only thing that changes is the limits. So what is the antiderivative of 1 minus x squared? We're going to use the reverse power rule and the reverse constant multiple rule. So it's going to be x minus 1/3 x cubed. Okay, now for our first definite integral, we're going to be evaluating that from -2 to -1. Okay, and again, don't forget to put your absolute value bars around that because you're going to have to value that for total area. Again, the antiderivative won't change for any of these pieces. The next one goes from -1 to 1. And finally, we're going to take the absolute value of the definite integral of the same thing from 1 to 2. Okay? Just realized my notation looked a little bit weird. So my definite intervals are going to go inside of my absolute value bars. Such, my absolute value bars will go outside. So anyway, let's evaluate this now. I'm going to go ahead and write that out. I'll pause this and come back and explain it. Now there's different ways to solve this. I'm going to solve one piece at a time. So I'm going to figure out this first definite integral and take the absolute value of it. So I'm plugging in my upper limit for the first piece and then subtracting when I plug in my lower limit. I'm plugging in -1 into my antiderivative, then I'm plugging in -2 and subtracting that. Notice I'm putting my brackets around to be careful. So I'll be right back with that evaluation. Okay, so this first piece is going to be -1 plus 1/3. I'm going to keep my brackets. It's going to become -2. The two negatives make a positive 8/3. This negative is going to distribute into both of these. It's going to be -1 plus 1/3 plus 2 minus 8/3. Now, -1 plus 2 is 1. I'm going to write that as 3/3 because for my other part, it's going to be minus 7/3. 3/3 minus 7/3 is -4/3. If I take the absolute value of that, I get 4/3, which confirms from my graphically that we got positive 4/3 for this total area. And again, I'm taking the absolute value because we're worried about total area, not net area, which is the definite integral. All right, so I'm just going to do the same calculations for my other two pieces, and we'll show that, and then we'll move on and talk about total area versus net area. So for my second piece, again, we're plugging in the upper and lower limit into that middle piece. I'm going to plug in 1. I'm going to get 1 minus 1/3. And then I'm subtract when I plug in my lower limit, so it's going to be minus brackets -1 plus 1/3, because this is going to be two negatives down here. It's going to end up being 1 plus 1 when the negative carries over, minus 1/3 minus 1/3, which equals 2 minus 2/3, which also equals 4/3. All right, let's take a look at the third piece. Again, this is for total area. For my third piece of my function and its area under the curve, I'm going to plug in 2 for my upper limit, and as you can see, we're running out of room here. I'm going to plug in 1 for my lower limit for that and evaluate. I'm going to get 2 minus 8/3 minus 1 plus 1/3, double negative right there. And I get the same thing as I did with my first piece, which was 1 minus 7/3, or 3/3 minus 7/3. And again, we take the absolute value of that for total area, get positive, we get 4/3, which again just confirms this last piece of the graph. It's going to be positive 4/3 for total area. Remember to be negative for definite interval, which is net area. So if you didn't remember already, we've kind of already done this. You're going to take the absolute value of each definite interval. So if you've forgotten to do it, basically what that would look like is negative 4/3 for the first one, take the absolute value. The middle one was already positive, we'll just go ahead and take the absolute value of that since it won't matter. And then the third one was negative. So if you just want to take the definite integral for step 4, you can. Just don't forget to take the absolute value for step 5. Okay? And then step 6 is just going to sum up those absolute values. So that, for the first one's going to be positive 4/3. The next one's going to, whoops, doesn't need to be the absolute value anymore. The second one's going to be positive 4/3. And the third one's going to be positive 4/3. And if you 3 times 4/3, you actually just get 4 back. And that will give you the total area between the curve of 1 minus x squared and the x-axis from -2 to 2. The key here again is to find your x-intercepts. Split this up into different definite intervals. Find the definite integrals individually and take the absolute value of each of them and then add them up, which will give you the total area to the curve. Now, as a reminder, what does total area mean in terms of practical application? It's pretty much the way I remember is the difference between total distance traveled and displacement. So if you run around a track 4 times and run a mile or a kilometer or whatever, you really haven't gone anywhere as far as changed your location, but you have traveled a total distance. This is what total area means, and in that case you would have ran a total of a kilometer or a mile. We'll get into that more when we talk about particle motion. If you have any other questions about this total area example, let me know.